In this lesson, we will talk about the last two inverse trig functions that have yet to be discussed, arctangent and arccotangent. Arctangent is going to be one of the most useful and used functions in trigonometry, and it will have a lot of conveniences to it that some of the other inverse trig functions do not. On the flip side, arccotangent will be relatively inconvenient, particularly how it relates to arctangent, but we'll talk about that momentarily. To start off with arctangent, just like with the other inverse trig functions, we need to take a portion of the original function of tangent that will pass the horizontal line test, so we can make an inverse out of that. Tangent, just like sine and cosine and secant and cosecant, is periodic by nature, which means if you draw a horizontal line through it, you will hit the function multiple times. Therefore, the full inverse will not itself be a function. We need to only take a portion of it. However, if you notice, tangent is a little bit unique compared to sine and cosine. It does not have any portions where it curves back in on itself, similar to a parabola or a function to a higher power. In this case, these functions, if you look at tangent that has a bunch of asymptotes, the sections between the asymptotes already are functions that are one-to-one. They pass the horizontal line test at every juncture. So the portion that we're going to take for arctangent is actually relatively convenient. It will be the portion from the first asymptote at negative pi halves to the second asymptote at pi halves, at least first and second in this drawing. That is where we're going to get the function for arctangent that will have horizontal asymptotes at negative pi halves and pi halves, and we'll have this curve that kind of looks like a logarithmic function that approaches these asymptotes. Now, one of the nice things about arctangent is its domain. Compared to arcsine, arccosine, and arcsecant and arccosecant, all of those, we need to be careful that whatever value you're plugging into the inverse function actually defines a realistic triangle with relation to the hypotenuse side. For example, for arcsine, you needed to plug in a ratio that made sure the hypotenuse side was as big or larger than the opposite. So you couldn't plug in anything larger than 1. Arccosecant was the opposite of that. You had to make sure the ratio was 1 or larger to define the hypotenuse to be larger than the opposite side. The same is true for arccosine and arcsecant. However, for arctangent, the ratio that tangent refers to is opposite over adjacent. There are no restrictions for how the opposite and the adjacent have to compare to each other. One doesn't have to be larger than the other, meaning you can really take on any ratio, and therefore the domain, as seen from the graph of arctangent, and when you think about the input being the ratio of opposite over adjacent, is all real numbers. You can plug anything into arctangent and you will get an answer back, which is relatively unique among most of the inverse trig functions. That's one of the more convenient things about it. So you don't really need to be too worried about, does this define a realistic right triangle? For the range, on the other hand, the range is more restricted. It does not go for all real numbers. As seen from the graph here, our range is restricted based on the asymptotes we have. The asymptotes that we have, though, at negative pi halves to pi halves should sound relatively familiar because that's very similar to the range we had for arcsine, which was negative pi halves to pi halves, both inclusive. The only difference here for arctangent is that we have asymptotes at both of those values. It's not inclusive, it's exclusive. So it's still negative pi halves to pi halves, but with open brackets there. That also is kind of nice when you compare that to arcsecant and arccosecant, which have asymptotes that go right through the middle of their range. A little bit annoying to work with there. Another convenience about arctangent. Arctangent is an odd function, just like arcsine and arccosecant, which means when you have a negative input on arctangent, you can pull that out in front of the function and have a positive input instead. That's also pretty nice. When we have odd or even functions, and we can manipulate in that manner to make our lives a little bit easier or to use negative numbers a little bit less, then that is convenient. Now, the part about the domain being convenient, that comes into play with the first line we have for other information here. Tangent of arctangent. When you're doing tangent of arctangent, that will give you x, but unlike all the other inverse functions when we had this kind of definition, sine of arcsine, cosine of arccosine, etc., this is true for all x. So tangent of arctangent will just cancel each other out in all circumstances. That is very, very, very convenient. However, the other way is still just like the other trig functions. When you take arctangent of tangent, that will not always just cancel out to give you x. That will only give you your input on tangent back if that input is between negative pi halves and pi halves, non-inclusive. So if you're doing, say, arctangent of tangent of pi thirds, sure, that will just give you pi thirds, because pi thirds exist between negative pi halves and pi halves. But if you're doing arctangent of tangent of, say, 2 pi thirds, that will not give you 2 pi thirds, because 2 pi thirds is not between negative pi halves and pi halves. Instead, if you work from the inside out there, tangent of 2 pi thirds ends up being negative square root of 3. And arctangent, which works with angle measures from negative pi halves to pi halves, or in the unit circle, quadrant 1 and 4. This will give me an angle measure in quadrant 4 instead. Specifically, this will actually give me negative pi thirds back. So still an angle measure in the same family, per se, of pi thirds. In this case, it gives us negative pi thirds. But it's not going to give us the exact same answer of 2 pi thirds back. So still be careful of that when you apply an inverse function to that trig function itself. Let's move on into arccotangent now. Arccotangent, which is going to be the inverse reciprocal function for arctangent, is going to have a lot of similarities with both how arctangent works and also how the other inverse reciprocal functions of arcsecant and arccosecant work. Let's start with where arccotangent comes from. Just like all the other inverse functions, we want to take a portion of the original function that passes the horizontal line test. Thankfully, this works just like tangent does, really, where we can take a portion that's between asymptotes because this curved shape is itself going to pass a horizontal line test at every juncture. So we could just take the portion between a set of asymptotes. The set of asymptotes that we will use here are the set of asymptotes from the y-axis at 0 up to x equals pi, which means that our inverse of arccotangent will have asymptotes instead at y equals 0 and y equals pi. And then we have our curve that approaches these asymptotes and goes on for infinity. So that means the domain for arccotangent is actually going to end up being the same as arctangent. The domain for arccotangent and arctangent are both all real numbers or negative infinity to infinity, meaning you can still plug in any ratio. Cotangent is supposed to be adjacent over opposite. There are no restrictions for how those two side lengths in a right triangle need to compare to each other. So there is a convenience there for arccotangent. But we're going to go through a couple other properties here that are going to demonstrate some inconveniences about arccotangent. Starting with the range. The range, in this case, is from 0 at the bottom of our asymptote to our top asymptote, which is at pi. That means our range is from 0 to pi, non-inclusive. Why is that inconvenient? because arctangent also had a similar kind of setup and no asymptotes in the middle. And I said earlier that was actually pretty nice. The reason that this is inconvenient is because it does not really overlap well with arctangent. If you look at, say, arcsine and arccosecant, arcsine has a range of negative pi halves to pi halves inclusive. Arccosecant, the inverse reciprocal, is negative pi halves to pi halves with one value in the middle cut out at 0. But that still means that the ranges overlap per se. They still cover the same quadrants of the unit circle. For arctangent and arccotangent, that's not true. For arctangent, it's from negative pi halves to pi halves non-inclusive, whereas arccotangent here is from 0 to pi non-inclusive. That means arctangent can result in answers in quadrant 1 or 4 of the unit circle, whereas arccotangent can result in angle measures from 0 to pi, which is quadrant 1 or 2. That's a problem when we start to try to consider how to go back and forth and change a function of arccotangent into a function of arctangent. Not going to work as smoothly as it did for the other inverse functions, for, say, arcsecant into arccosine or arccosecant into arcsine. That's the problem here. The ranges are not the same. This is also demonstrated with the symmetry. The symmetry for arctangent was odd. And for arccotangent, doesn't have any. You cannot flip this over the y-axis. You cannot rotate around the origin 180 degrees to get to the right position. So this does not have any symmetry, which is another problem. That means that you cannot adjust any inputs on arccotangent that involve a negative x per se. So let's go through the other information that demonstrates why arccotangent is a bit inconvenient. All right, starting with the top. The top line is nice. Cotangent of arccotangent, that will give you x for any x, because there are no problems with the domain for arccotangent. Plug anything into arccotangent, there are no problems there. However, when you do arccotangent of cotangent, that will only give you that value of x, the angle measure you plugged into cotangent, back if that angle measure is between 0 and pi. We've demonstrated a number of these examples before, but if you do arccotangent of, say, cotangent of, I'll do 5 pi over 4, this will not equal 5 pi over 4. As demonstrated before, work from the inside out. Arccotangent of cotangent of 5 pi fourths, which is a positive 1. This will actually result in an angle measure between 0 and pi. Positive would have to be quadrant 1 in the unit circle then. You'll actually get pi fourths back from this. So not 5 pi fourths. The more important thing that I want to address here, because that has been touched upon in just about every inverse reciprocal function. When you work with arccotangent and you want to try to approximate that, say in a calculator, if the ratio you have is positive, then that means arccotangent will give you an answer back between 0 and pi halves, somewhere in quadrant 1 in the unit circle. If you did that in arctangent, a positive ratio should also give you an angle measure from 0 to pi halves, which means you can change arccotangent of x into arctangent of 1 over x to take the reciprocal of the ratio of sides. That works just fine, just like it did for arcsecant and arccosecant, if you're dealing with a positive ratio. So that's okay. But if you're dealing with a negative ratio, there are some problems. This is where the lack of overlap of range comes into play. Arctangent would take a negative input and result in something between negative pi halves and pi halves, something in quadrant 4 of the unit circle. However, a negative input on cotangent, or arccotangent, will give you an angle measure between pi halves and pi, which is in quadrant 2. So, technically, if you want to try to evaluate arc cotangent of x, where x is negative, meaning we expect something in quadrant 2 of the unit circle, you can still apply arctangent of 1 over x, but keep in mind that arctangent will not give you an angle measure in the right region. If you want to get an angle measure from quadrant 4, say this angle measure, this negative angle measure, and you want to result in this thing that has the same reference angle in quadrant 2, then what you need to do is take your angle measure in quadrant 4 and add pi to it, or add 180 degrees if you're in degree mode. So if you're dealing with a negative ratio with arc cotangent to get something in quadrant 2, you can apply arctangent in a calculator, but you do need to add pi in order to get to the right ratio. That's one of the most inconvenient things about arc cotangent, the fact that it does not overlap with arctangent. As a quick example, if you wanted to do, I'll just do -1 as an input. If you wanted to solve arc cotangent of -1 in a calculator, because you could do this one by hand, arc cotangent of -1 should give you a ratio between 0 and pi. This negative, it would have to be quadrant 2 of the unit circle then. This would actually give you 3 pi over 4. But if you try to just do this as arctangent of 1 divided by -1, and you evaluate this, this will not give you the right answer, because this will give you pi over 4, or negative pi over 4, because arctangent is only defined from negative pi halves to pi halves. If you need to use a calculator for approximation purposes and change arc cotangent to tangent, you have to keep in mind that after you change into arctangent, you're dealing with a negative ratio, you have to add pi to your result. That will give you negative pi fourths plus pi, which will give you the same answer. So that's a quick example demonstrating how you would use arctangent to solve something for arc cotangent.